All right, I'm conscious that I'm standing between you and your conference dinner, so I will try and keep this snappy. Unfortunately, we've had a very good introduction to this general area of physics from Sarang just an hour ago. And of course, it's great to be here. This is, you know, it's a great thrill for all of us to be talking to people face to face again. And so thanks to the organisers for being taking the step and putting this on. And also give a special thank you to my daughter Felicity, who, being an American citizen, got me into the country despite the travel ban. So completely legally, so it's fine. The work I'm talking about today is collaboration with Peter Kleiss. He's a postdoc in Cambridge, and he's been doing all sorts of fantastic things over the past couple of years, including growing this marvelous beard for the people who haven't seen him recently. And the other person here on the right is Jonah Hertzog-Arbeitman, who is a master's student for a year in Cambridge, and he's now moved on to graduate school at Princeton. If you want to follow along or click on any of the links, these slides are addressed down there in the bottom. Okay, so what I like about this problem is that it's really simple to state. It's sort of embarrassingly simple problem. You take something like a Heisenberg spin chain, spin 1/2, higher spin, classical, we'll talk about as well. And you ask, what's the nature of spin transport in that system? At finite temperature, or infinite temperature, as what we can find to most of the time in this talk, all three components of the spin are conserved. Your default expectation would be that spin diffuses at finite temperature and at infinite temperature. And of course, these questions have very long history. I mean, those models, of course, are very old, and the corresponding questions are very old. And some of that history is summarized in this fantastic book by Forster from the 70s, I think, or end of the 70s, all about hydrodynamic fluctuations and correlation functions. And it contains this, you know, after the introductory chapter, chapter 2 is a simple example, spin diffusion. So, you know, for any students watching, you know, anytime you see this word simple in a book, you can just ignore it because nothing's simple. We're still talking about it all these years later. And of course, what's complicated, or what can be complicated about this problem is that the spin is non-abelian. We can be in low dimension, where fluctuations are strong, and you've got the question of integrability as well, all these things that you've seen already in Sarang's talk. So I'll just go over, now the question of transport is just a very long history and very controversial, and people arguing about various different possibilities. I just want to go over some the more recent predictions that we've seen in the last year or so, or last few years. I would say there's now very good evidence, numerical, theoretical arguments of the kind Sarang gave, experimental as well, as he told us at the end, for support for this KPZ-ish scaling behavior, that distance scales go like time to the 2/3 instead of like time to the 1/2 for diffuser systems. And this seems to be special to integrable non-abelian models in one dimension. It could be classical or it could be quantum. And he mentioned this recent review that he's written with 2 other people, which summarizes the state of the art from a couple of months ago. Now, when you dispense with integrability, things are probably not so clear yet. So there's a paper here from last year, which was about the classical Heisenberg chain. So unlike the continuum Heisenberg model, which has the Landau-Lifshitz equation as its equation of motion, just taking that Heisenberg lattice and taking those spins to be classical spins gives you a non-integrable model. So you don't get that KPZ scaling. And this paper found on the basis of numerical simulations or surmised a diffusion constant which grew with time, like log t to the power 4/3. So still super diffusion of a kind, but weaker than the kind that's seen in the integrable case, in the KPZ case. This is some work from just in August. Again, numerical work on you know, even larger systems. Again, it's the classical Heisenberg model. And this one points to some, at finite temperature, a difference between the ferromagnetic case and the anti-ferromagnetic case. At infinite temperature, you expect them to be the same. At finite temperature, they could potentially be different. And what this finds is that sort of different from how things are at 0 temperature, it's the ferromagnet that looks anomalous at finite temperature, and seems to have this KPZ-ish scaling.
Sorry if you said this and I missed it, but this is a classical model. What's the dynamics you're using?
So it's the Landau-Lifshitz equation.
Oh,
yeah. So which in the lattice case is not integrable in 1D, the simple version. Whereas the antiferromagnet looks normal, apparently. And so this is obviously different from what we just saw on the previous slide. Sarang talked about this paper of his. So this is Donadis et al. It's a different, same Donadis, different et al. I think from this year, about the noisy exchange model that Sarang introduced. And this is where you see a logarithmic growth of diffusion with time. So again, it's a weaker superdiffusion. And this is the model I'll be coming back to. Now, the issue, of course, is I hope that wasn't reflective of the audience. That's me. That's my work day. It's finished now. So this is okay. I really should move faster. So the issue, of course, is we don't really have good tools when we throw away integrability. We have arguments about based on weakly breaking integrability that Sarang reviewed. This is not yet a systematic tool. It's something that one can deduce scalings and so on, but it's not like like perturbation theory or something like this that one can carry out to every numerical factor. At least I can't. And of course, there are no small parameters because we're interested in the isotropic case, so we can't take a large anisotropy or something like this. There's only one scale, which is the exchange coupling. Okay, so what we'll be looking at is this noisy exchange model that these guys introduced early in the year. And the point is, as has already been mentioned, it's got SU2 invariance still, but we throw away energy conservation. And because of that, we only expect to have in the hydrodynamic limit, just spin mode hydrodynamics rather than energy density hydrodynamics playing a role. But the real reason I'm so interested in this model is that you can actually develop a perturbation theory in J in this case, and you can just do everything. And that's pretty useful, I think, when you're dealing with something which is, has a sort of long history of controversy and different methods and so on, is to just have some simple results. To be honest, when we started this project, I thought this is a way to get into superdiffusion, to capture superdiffusion in perturbation theory with everything under control. What I'll tell you is that actually it's not diffusive, at least within the perturbation theory that we've done. It's not super diffusive, at least within the perturbation theory we've done so far. We just get regular diffusion, but with some interesting features. Good. So what we're going to calculate is correlation function. So you have spin half system, n sites, and we're interested in the infinite temperature correlation function of 2 spins. You evolve one forward in time in the Heisenberg picture, take the trace, no Boltzmann factor because we're at infinite temperature. Because we've got SU2 invariance, there's just the spin indices just have a Kronecker delta, and conservation means that when we sum over, we've got two spatial coordinates J and K. When we sum over K, we get 1 at all times. That's spin conservation. So for now, we'll just fix the spin indices to be Z, and we're just going to imagine propagating a single Z operator. Now, the way we usually handle things in these sort of infinite temperature calculations that have become popular in recent years is to do an expansion of that evolved, Heisenberg evolved Pauli operator in the Pauli basis. So we have some coefficients which weight each possible combination of Pauli operators each side, including that's the X, Y, Z, and the identity operator at each site. And so our expansion is written in terms of those coefficients. And so if we want to start from a single Z operator at one site, then all of the coefficients are equal to 0, except for 1, and that corresponds to when we have identity operators everywhere, except for one site where we have a Z. And that's our initial condition, and we evolve that thing. The C's evolve, and then to evaluate the correlation function, we pick out one final coefficient, which corresponds to when all the operators of the identity except for one at site K, and that's our correlation function. Okay, so that's the thing we want to calculate. So now I'm writing the same model in a bit more mathematical language as a stochastic Schrödinger equation. So now instead of writing it in terms of spin operators, I write it as an exchange operator, so it just swaps spins on two neighboring sites. And that's weighted by the exchange coupling J, together with some white noise fluctuations, dW. Those are increments of independent Brownian motions at each site. Now, those of you, actually, we saw this, I think, in Sebastian Diehl's talk. The last term may have you scratching your head if you haven't seen this before. That's there to actually ensure that the norm of the wave function is preserved. It's a consequence of interpreting this as an Ito-stochastic differential equation. If you then ask what the equation of motion for the Heisenberg equation of motion looks like for that system, it's an exercise in Ito calculus to come up with this equation. So the first part looks probably familiar. It's just a von Neumann equation, commutative P with the operator. And then the second part is this Lindblad-like term, which knows about the exchange operator. It's still got the white noise in it, the DWs. If you're interested in the average of the operator, you take the expectation value, use the fact that these DW increments are independent of the current time. They're a step into the future. So when you take the expectation value, you drop them and you end up with this equation at the bottom for the evolution of an operator, and this is the main equation we'll be studying. If it's a bit slick to do this sort of stochastic calculus Ito business, let me give you a more pedestrian derivation, which is the way, of course, we did it first time. So we're used to these days thinking about dynamics in terms of unitary gates acting on pairs of sites. So a SU2 preserving gate is given by this unitary here, parameterized in terms of some cosine, so cosine of the times the identity minus I sine times the exchange operator, with some parameter theta, which determines how far from the identity we are. And you imagine performing some step of time evolution on an operator just by applying a U dagger and a U on either side and multiplying that out, and you get this expression here, a term with cos squared, term with sine squared, term with sine cos. Now, imagine that your thetas are random and take values plus or minus theta 0 randomly. Then you can see that that randomness is not going to affect the first two terms because they're even, but it will affect the last term, which is odd. And if you bias that distribution, so you're a bit more likely to be plus theta than minus theta, then the last term will survive, but it will be small in that bias. So if you do that average, then this is what you find, and indeed the last term is proportional to delta of this bias. And so the interpretation of this is that the operators on sites j and j plus 1, they switch with some probability sine squared theta naught, but this asymmetry delta leaves behind a trace of, if you like, the quantum dynamics, which knows about the commutator. And then if you take this limit, written at the bottom here, that theta naught goes like square root dt, and delta goes like j square root delta t, you just get back the continuous time limit, the equation that I showed you a few slides back. Okay, so this is sort of the key to the method. If you set j equals 0 in this, which is that's the strong noise limit relative, so the noise is strong relative to j, you're just left with the last term here, and that's just a master equation, which tells you that the operators basically evolve by random transpositions. So you pick two neighboring sites and you switch the operators. And obviously that preserves subspaces which correspond to fixed numbers of operators. So you've got a fixed number of x's, a fixed number of y's, a fixed number of z's, a fixed number of identities, and these just get switched around by this dynamics and transposed randomly. And then we can think about adding in j as a perturbation into that picture. So let's keep it 0 for the time being. If we have the one operator sector, so that means everything's the identity apart from one site, you have an x, y, or a z, then you can write down an equation of motion just in that sector, and that equation of motion wouldn't surprise anyone, is just a discrete random walk. So you just get the discrete Laplacian appearing, and so that describes the diffusion of a single z operator. Likewise, if you went to the two operator sector, so you introduce an x and a y, those x and y are going to diffuse. There's obviously something interesting which happens when they are on neighboring sites. because they can't sit on top of each other, but they can switch places. So that's why that last term is there. That's just consistent with sort of hardcore conditions. So it's a Markov process, but one where they don't sit on top of each other. This is all j equals 0. And now what happens when we turn j back on? You have to compute the commutator of p with whatever can happen, whatever operators you could have at two neighboring sites. So you could either have identity, that's obviously not very interesting. You could have Pauli identity, or you could have Pauli on two neighboring sites. And you compute the commutators, this is what you get. You get epsilon symbols appearing, obviously. And the one simple thing to say about this is that the spin conservation sort of rears its head here, that if you imagine adding the first two together, that would be adding up the total spin on the two sites. And so you get 0, it's conserved. But the more interesting sort of dynamics which is implied by this is that one operator or one non-identity operator gives rise to 2, and 2 gives rise to 1. So that we have a picture where operators split or they merge in perturbation theory in J. And so if you write the equation of motion in component form, it looks like this. So the last two terms are just describing this random transposition process. And then the J term is giving us this operator splitting and merging. And the point is the averaging has given us the freedom to balance these two terms separately. I mean, if we didn't have noise, we wouldn't have the last term, and we would just have J sitting there by itself. And if you think of what this picture would look like in that case, it would be thick with operators as time progressed. But by dialing down J relative to the noise, you can have a rather sparser picture like this, where things diffuse for a long time before they split or they merge. And that gives you a controllable perturbation theory parameter. And also suggests a simple approximation, which is you just keep track of one operator and two operator sectors. So an operator can split, and then it merges again, splits and merges. And you get that by taking your equation of motion and just throwing away the possibility of generating a 3-operator sector. Yep.
So without J, there is no operator growth, like out of time order correlations will not have chaos, for example, and J is what really fixes the Lyapunov exponent.
Of course, in any realization, there is, but on the average, there isn't.
Right.
So, but that's okay, because if you care about a correlation function, you can average over the trajectories. But yeah, obviously all of that, entanglement is growing, but it's all, from the point of view of correlation function, it's all averaged out.
Actually, I have a question. Is there a limit in which you can get the energy increase?
If you can get the which equation?
There must be some way to get the classical equation of motion.
Yeah, I sort of think that this is morally equivalent to basically a noisy dissipative Landau-Lifshitz equation, I think. Okay, so this approximation is simple enough to push all calculations through, and it really amounts to one loop lowest order calculation of a self-energy. So the correlation function is expressed in terms of this self-energy. Self-energy is this loop summation where omega is the eigenvalues of one-dimensional Laplacian. And the sort of the non-trivial aspect of this is the structure of the vertex, which, as you can see, is in the numerator there, has got some momentum structure, also has some spin structure, if you remember. The hardcore constraint that I mentioned, this is sort of a parenthetical remark, that the operators don't sit on top of each other. That makes it look like they are interacting particles, but they interact in the sort of it's that symmetric wave function, which is affected by that hardcore constraint, whereas the vertex that we just introduced is actually anti-symmetric, and so the hardcore constraint doesn't do anything in this calculation. All right, so you can evaluate that self-energy. We're interested in the hydrodynamic limit, where the dispersion is quadratic, so long wavelengths, and omega is of order eta squared, wave vector squared. The self-energy takes on this very simple form. What that means is that the diffusion pole.
Sorry, I'm lost. Okay. The dispersion of what?
Dispersion of the single operator. So the.
Oh, I see. Because it's a random walker.
It's a random walker. Okay. Yeah. So it's just it just has quadratic dispersion, or it's a time-binding model, but we're interested in the low Q limit. So the behavior of the structure of the correlation function is the diffusion pole, which appears at minus I eta squared, becomes a pair of poles where the coefficient of wave vector eta squared is renormalized, and there's also an eta cubed term which appears, which is real, plus or minus. And there's also a branch point in this thing starting at minus I eta squared over 2. And that's actually the same structure which appears in this paper from the hydrodynamic perspective, so the kind of thing that Andrew Lucas was telling us about this afternoon, a hydrodynamic rather than a microscopic theory. And the way to understand what's going on here is quite simple. Because of this cubic vertex, a diffusive mode can split into 2, and obviously the lowest frequency that can have, consistent with the conservation of momentum, is if the 2 modes have half the momentum of the initial mode. They've got quadratic dispersion, and so this 2 diffusion branch cut starts at half the value of the bare diffusion pole. So, okay, so it's sort of, it's all looking reasonable, but now we can just calculate what happens to the diffusion constant. And so as you can see, this starts at eta squared. So J is just enhancing ordinary diffusion at this order of the calculation. And you can go further and find the transient behavior of the diffusion constant just from this formula, which just keeps track of the width of the correlation function, how it changes with time. And you get a nice closed form expression involving Bessel functions, but in the long time limit, you get this behavior. So 1 plus J squared is the long time behavior, and then you get this approach that goes like 1 over square root T. So we did some numerics to check this out. It's, I guess, a relatively standard tool, so representing Z as a matrix product operator. I think Sarang mentioned this point already, that as you turn the noise up, so this corresponds to small j in this thing, then it's very easy to simulate because the operators don't spread, or they don't multiply, they don't branch, and so at j equals 0, you have a single operator diffusing. You can represent that exactly by a matrix product operator with bond dimension 2. As you go away from the j equals 0 limit, bond dimension obviously has to grow, but it's sort of under control. So how does it look? You can see this transient behavior of the diffusion constant we just derived. So the dashed line is the analytic result, and so at low values of j, the numerics are very, very much consistent with the result. Obviously, big things begin to break down at higher values of j, but the analytic calculation is sort of providing an upper bound on that. So we supports the idea that there's no, at least strong noise. So just to emphasize, this is the opposite regime to what Sarang was talking about. As you back away from strong noise, you seem to see enhanced diffusion, but not super diffusion. One other thing you can look at is the profile, the diffusive profile. So if you assume that the poles dominate the correlation function, you can do a saddle point analysis, and you can find how the Gaussian spreading diffusion is modified by the presence of J, and you get this result here, which has a sort of rather tantalizing KPZ-ish like quality. It's got its mod x cubed over T squared, which looks a little bit like what you would expect from basis KPZ, but of course it's sitting on top of this diffusive behavior. So possibly a coincidence, possibly not.
Can I ask you a simple question? So if you use not the asymptotic D, but like transient D, can you get?
But what is?
It's function of T, right?
Yeah.
Transient. So if you plug namely D of T there, you will get. Can you get just universal power out of this? At infinite time, of course, you recover diffusion like present tense, but if there is universal growth, I'm just curious, is it consistent?
Well, I guess. Well, I wouldn't have any justification for doing it because I guess this thing is derived in the infinite time limit, which D is just the 1 plus J squared enhanced value. I mean, so you would, if you wanted to do it sort of properly, so to speak, you'd have to do a real, the perturbation theory calculation, but with a finite time horizon. I mean, you could probably, actually, sorry, I will show, maybe I'll show it now. So you can integrate those equations, sorry. You can integrate the truncated equations in finite time, and this is what you see. So the line, the continuous line is the fit to this approximate expression, and then there are two data points, or two sets of data in this profile. One is the matrix product operator calculation, one is the perturbative calculation, but integrated in time numerically, and they're on top of each other. So, and this profile, doesn't quite fit, but it fits better as time progresses. So the agreement, yeah. So this one is, yeah, this is something nice to look at, but if you integrate the perturbation scheme, you get basically bang on agreement. So. Yeah, the other connection that you can make with this approach is to hydrodynamics. So there's a paper last year which motivated by these spin chains, dealt with non-abelian hydrodynamics and asked about whether there were possible ways of understanding on a hydrodynamic basis these results about anomalous diffusion and so on. And the general conclusion of that work, I think, at least with regard to spin chains, was that the hydrodynamic perspective says things should be diffusive and allowed for possible corrections arising from corrections to the current, which look like this. And this is really the same structure. Actually, it's not right. There's a gradient missing from here. Sorry, I've missed it. Yeah, there's a gradient missing from the second term. If it was there, that's exactly the same structure as the vertex that we find microscopically, which is reassuring. And this result implies lambda squared over root T corrections to the diffusion constant, which is exactly what we see in our theory and in our numerics. So I think it's sort of consistent with that hydrodynamic picture as well. Higher orders, well, so this second order result had this branch point which is arising from the disintegration of one diffuson into two. So on purely kinematic grounds, you can say that if you went to order j to the power 2n, you would get a branch point starting at minus I eta squared over n, which was when one diffuson disintegrated into n diffusons, which are all at the smallest momentum, eta over n. There is a sort of interesting argument published. Sarang pointed this out to me, published last year in this paper, which goes by the name diffusion cascade. So if you try and estimate the contribution to n diffusons arising from these higher order processes, then you'll have some estimate which looks like this. And then if you just find what is the optimal n, so as time progresses for fixed value of wave vector, what is the optimal n which contributes? And if you believe these estimates, then that gives you a contribution which has this stretched exponential form. So it still has the same z equals 2 behavior, but it has this interesting stretched exponential. And as far as I know, there's no microscopic model in which this has been observed, but it would certainly be interesting. How long do I have? Okay. I'll just, this won't take 5 minutes, but I'll close with a sort of amusing feature of the perturbation expansion. You would have to be interested in summing lots of diagrams to make use of this, but it's kind of fun in any case. So as you've seen, this vertex that describes the operator splitting and merging has got an epsilon symbol associated with it. And it turns out that graphs weighted, where the vertices are weighted by this epsilon symbol, actually turned up in some work of Penrose in the 70s or 60s, and they're related to 3 colorings of the graph. So basically, if you count the number of ways that the number of contributions with you sum over all indices on the lines associated with this epsilon symbol, then for this graph at the top you get 6, and all these colorings are illustrated on the bottom. So you can imagine red is for X, green is for Y, cyan is for Z. And so if you did want to go to this model and sum up really complicated diagrams, you would find yourself having to solve this kind of coloring problem to figure out what the contribution from doing all the contractions was. some graphs can't be 3-colored, so you would get 0 if those appeared in perturbation theory. Some graphs which are non-planar, you do the same thing, although they can be colored because of the signs and the epsilon symbol. You get 0. You'd have to be interested in going to very high orders to be motivated to do this. But okay, good. That's all I wanted to say. Thank you.
I'm wondering if the reason you didn't get the superdiffusion is because your perturbation to integrability was big.
Yeah,
it was basically that. Okay.
Yeah, so I sort of hoped that it would be. I sort of hoped going into it that maybe I didn't know as much about superdiffusion. I sort of hoped that maybe you didn't need to be close to the integral point. Maybe the non-abelian symmetry was enough. And so I think this sort of convincingly shows that that's not enough. Yeah.
I guess as a comment to that comment, I feel like, if there were a universality class with this log enhanced diffusion, then it should not depend on sort of having perturbatively weak integrability breaking. So, well, I guess the chain itself already is sort of not integrable. So, yeah.
You'd be stuck in this kind of pretty undesirable territory of having to have like a log enhanced behavior at small j and then no enhancement at large j, and then having to try and figure out something happened.
The other comment I would make, I don't recall seeing this plot, but maybe I missed it, is that in our work on this with Pauli et al., I mean, if you actually take those plots, like we were able to get log plots that look like they have log enhanced diffusion, exactly like Denardis et al. But then I thought you replot it in a better way, and you keep track of what the actual long time tails should be, and you find that actually that log enhancement is just like a very slow long time tail. So I don't even think that log is there anywhere. So just to be a bit aggressive and on the record, but yeah.
It's not my log.
I mean, you could try and find out what was wrong with our perturbation theory, I guess.
So if I understood correctly, most of your results are basically leading order in perturbation theory.
Yeah.
So I guess the way in a calculation like this, the superdiffusion, the way it would show up would be somehow a breakdown of perturbation theory that doesn't convert like you.
Yeah. So
is that still a possibility, or?
Well, I sort of always hope for a breakdown at first order in perturbation theory. So maybe, but it would have to be fourth order. So, but please, somebody do it. Yeah.
So maybe a way to do it non-perturbatively, if it's not the issue that it's a big breaking of integrability, is can you have a large n version of this where
so you can. I mean, so you could, for example. I mean, it's completely straightforward to make that SUN because it's just an exchange. Is that what you were thinking of?
That's one way, but I was thinking of leaving it SU2 and having an auxiliary degree of freedom that would give you, and basically maybe have interactions inside each one of your unitaries in SU2 sectors.
Okay. So I thought you were going to say large S.
It would be neither large S or large N,
so maybe
but we can discuss because I want to leave the SU2. I think it's somehow...
Unfortunately, neither large N nor large S produce something super nice because they tend to lead to operators which quartic interactions as well.
But we actually needed that, so we actually recently formulated a large N theory where we leave the large SU2 intact and just have an auxiliary degree of freedom. We can discuss that.
Right. Okay. Yeah, that sounds interesting.
Other questions? Okay, if not, let's thank all the speakers, including Dr.